Hey, this is Miss Logan. Today I'll be talking about sound waves and the Doppler effect. So far we have been really focusing on our transverse waves. So our transverse waves, we often say, go in this up and down pattern. So the actual particles are moving up and down the whole time. My propagation of motion, or my velocity, is moving perpendicular to that. However, in longitudinal waves, the points on this are just moving back and forth. The propagation of energy, or my velocity, is also moving that same direction. So we have that parallel motion. So in this type of wave, we have a series of compressions and stretches. Now, what makes sound waves unique is that density and pressure of the air, or any other medium carrying the source. So before we talk about that, when medium, we're talking about what type of material or object the sound wave is traveling through. So this could be something like water, this could be a room, this could be ice. There's a lot of different things that we could look at. So this medium that carries the sound are the quantities that actually oscillate. So what do we mean by that? Well, when a sound wave, which is shown here, is sent through this pile of beads, the beads actually oscillate, and you can see the compressions here and then the rarefactions here. So what's also unique is that the density and pressure affects how these sound waves travel. So really, when we're looking at sound waves, we have to focus on where are we, what is the temperature that day, and what is the pressure. Where are we? Here's just some examples of the different materials and how fast speed travels through. So for instance, if we look at aluminum, granite, steel, any of these things, our speed of sound goes through very, very quickly. However, when we're looking at air, it actually travels pretty slow, but this is typically what we're used to. So this is just kind of like a handy thing to have. However, if we ever do need, this is something we'd look up, not something we have to memorize. So sound waves can have any frequency. It just depends on the situation. However, our ear can only hear between 20 hertz and 20,000 hertz. With frequencies greater than 20,000 hertz, these are called ultrasonic. So sounds with less than 20 hertz are called infrasonic. So ultrasonic waves, we're used to these with medical applications. So if we think about an ultrasound to see a baby, we're actually using sound waves that are bouncing off the baby that we can actually see, quote unquote, the actual baby inside a woman. This is also how elephants and whales communicate. If we think about the movie Finding Dory, they talk a little bit about how certain whales can actually talk to each other using sound waves. They can communicate mostly in ultrasonic waves. However, sometimes they also use infrasonic waves. So these are our very low frequency waves. All right, so let's talk about how these sound waves interact with the world around us. So this is something that we call the Doppler effect. So the Doppler effect is the change in pitch of a sound when the source and observer are moving with respect to one another. So by that, we mean that when an observer moves towards a source, the wave speed appears to be higher, and the frequency appears to be higher as well. So if we think about the Doppler effect, we're also thinking about when we hear a siren. As a siren comes toward us, it actually feels like it's higher than it is when it's moving away from us. So let's look a little bit with the math of why this happens. Now, before we do that, remember that this wavelength is the known wavelength of the source that is creating that sound. The wave speed is how fast it's traveling. The observer speed, U, is how much that observer is moving. It's important to remember that we have to think in respect to the stationary source. So we're going to have some positive and negatives going on. So the new frequency that the observer hears it at is what we call frequency prime. So frequency prime says we have the two different speeds. So here we have the speed of the actual sound, and here is the speed of the observer, over V over F. So if we take a little bit of time and do some algebra, we can get a little bit simpler. So 1 plus U over VF. However, if the observer is moving away from the source, only the sign of the observer's speed would change. Now you'll notice that they actually change this for you. So when I'm talking about positive and negative, we can use either of these equations. However, honestly, we really only need to use this first one. However, if my observer is moving in the negative direction or away from the source, we would use U, negative U. So to summarize, F prime, so that's our Doppler effect frequency, is equal to 1 plus or minus, depending on moving away or moving towards it. U, so remember U is the speed of the observer over V, which is our known speed of those waves, times that original frequency. Our unit is still the same. We're using S1 over S or Hertz. Okay, so the Doppler effect for a moving source can be analyzed pretty similarly. Now it is the wavelength that appears to change. So this is the opposite situation. So the person is staying still and the sound is moving towards them. So we have our source speed, so that would be the car. We have our wave speed, which is the known wave speed of the actual sound, such as a car horn. And then we have our frequency. So in these problems, a lot of things are already known and will actually be given to you. So this looks very similar to our previous equation, however, it's a little bit different. So F prime, and remember, F prime is always what the observer hears, is 1 over 1 plus or minus, so this is depending if it's moving towards or away, U over F. U over V times F. Remember, in this situation, U is a little bit different. U is the speed of the source. By speed of source, we're talking about if it's a bicycle or a car, what's actually producing that sound. Okay, so let's look a little bit about how this looks in graph form. This is a comparison of the Doppler shifts for a moving source and a moving observer. The two are very similar at low speeds. Okay, so basically we're comparing these two equations. However, if we look at our orange right here, the source moving with the speed U, the frequency gets a lot higher. However, if the observer is moving with the speed of U, the perceived frequency does not move very much. If we just think about this kind of makes sense. When we hear an ambulance come towards us, it becomes very high frequency and then quickly drops off into low frequency. If the source moves faster than the speed of sound in air, which is about 330 meters per second, a sonic boom is created, which is this line right here. Okay, so if we combine our results, we can get our last and third case, which is the Doppler effect for a moving source and observer. So basically we combined these. So this speed is of the observer, and this other speed is actually of the source. So we have three different situations for Doppler effect, and make sure that you have all of them. Doppler effect is really important for weather, speed, medical diagnostics, and astronomical measurement. So let's see how this is used. So the Doppler effect shows a hook echo characteristics in tornado formation. So they actually look at how the echo, or how the Doppler effect is creating weather. Medical technicians also use Doppler blood flow to figure out the blood flow inside a person. So they're looking at how it travels and the relative speeds.